That's fine. I'll wait till it connects. That's fine. Okay, welcome everyone. Thank you for coming to the Royal Astronomical Society. My name is Lucinda Offer. I'm the Education Outreach Officer here for the RAS. Today we're here to welcome Dr. James Donoghue, who's doing our last RAS public talk of the season. He is a planetary astronomer and STFC Ernest Rutherford Fellow at the University of Reading. But I had the pleasure of first working with him virtually over COVID. We did some wonderful remote observations with him and the H3+ team at University of Leicester. But at the time he was in Japan because he was at the Japanese Aerospace and Exploration Agency, JAXA, as an international top young fellow. And he was also a postdoctoral fellow at NASA's Goddard Space Flight Center. His research involves the astronomy of giant planets, Jupiter, Saturn, and exoplanets, with recent astronomical discoveries making global news, which is one of the reasons why I asked him to speak with us today, because he has a passion for educating people about the wonders of space. He creates space science-themed animations, which are used in schools, planetariums, universities, and museums all over the world. His videos have over 250 million views across YouTube, Twitter, and other platforms, and have led to hundreds of news articles, which he will talk about today. And he was awarded the Europlanet Society Prize for Public Engagement with Planetary Sciences and a finalist in the American Association for the Advancement of Sciences Early Career Award and Public Engagement with Science. After today's talk, you can learn more about James if you don't already know. He has a fantastic YouTube page at Planetary with an amazing amount of videos for use for free. Please welcome Dr. James Donoghue.
Thank you very much for inviting me to give a talk today at the RAS. It's a real pleasure to be here, and great to see you, Lucinda, for the first time in person. We've definitely chatted a lot over during the COVID era, as we called it earlier. And today I'll be talking to you about my unexpected journey into animation. It's a bit of a riff on Lord of the Rings, but that's the only sort of Lord of the Rings reference in this whole thing. It's firstly, I'll be talking about let's just skip ahead here. Oh, this is where I find out that the slides won't work. So today, the slides might be a bit jumpy because this talk is about 1 GB in size. Okay. Okay, great. Thank you. There we go. So here we go. Let's start really, really far back. So at about 150 CE or AD, the standard view of the universe was that everything revolves around the Earth, and that's beautifully put into a diagram here, where you can see all of you see the Moon, Mercury, Venus, Mars, Jupiter, the Sun. They're all in orbit around the Earth in celestial spheres. This is a graphic from Cosmographia, which is from 1524. The cover of the book is just beautiful. I love this calligraphy. I feel like this is what I do sometimes. I end up not getting to the actual meat of the book or whatever I'm writing, and end up just fiddling about with the calligraphy. But yeah, so this was made by Peter Apian. So this tells you that basically all the way up to about 1500 or so, the prevailing view was that everything went around the Earth. It fits with everyone's common sense. It's what you see when you go outside, and it's what you see with the sun, and the moon, and the planets, and the stars. They're all rising and setting. Everything must be going around the Earth, right? So that's what this graphic is showing, and I think it's very powerful. So sort of fast forwarding, from about 1514 onwards, the Copernican revolution began. This is the idea that all of the planets actually orbit the Earth. All of the planets actually orbit the sun, and the sun is the center of our, I'll say, local universe. And so this is obviously the right answer, but you can imagine to change people's ideas on these major concepts back then, it was very difficult. So, it's challenging our basic common sense. Whenever I'm reading about this era, it really was common sense that everything went around the Earth. So to be able to convince people otherwise was quite a feat. That we're not, this special planet where everything goes around us. So it's a little bit difficult for people like Copernicus to convince people. So I think that they're showing this amazing graphic, publishing it. It took still maybe up to 100 years for it to be in common acceptance that this is the actual picture of the universe. And this is actually from the book. This diagram is actually from the book. I don't really speak Latin, I'll say that, but De Revolutionibus Orbium Coelestium, which sounds like a Harry Potter spell or something. But what that means is on the revolutions of the heavenly spheres. I just think it's really, really quite a beautiful, simple graphic. And it's one of the first examples where sort of a visual is used to get the point across very, very quickly. Because, I can talk all I like about how things are orbiting the sun, but until you actually see a picture of it, I think that's when you really start convincing people. And if you fast forward a little bit, this is at least one of the first kind of visuals that I could find that show you the scale of the planets and the sun in our solar system from 1698 by one Christianus Huygens, very famous astronomer. And this is what he had to say. The proportion of, so this figure was from his book. There's a lot of weird stuff in that book. I'm just going to say that. But this figure says the proportion of the magnitude of the planets in respect of one another and the sun. In the figure, you have the globes of the planets and of the sun represented to your eyes as placed near one another, which is just a fantastic way to say it. And actually, I copied and pasted that and put it onto Twitter the other day, as if then I quoted Huygens, because I just thought it's almost like it's designed for people online, to see it straight away, to understand it straight away, in a really quick way while we're scrolling and things like that. But yeah, this is a really, really good demonstration of scale. One of the first ones I could find. There are many more by Galileo as well. So I think of today, basically, science communication today, its purpose is really to intellectually enrich society. It also encourages people into STEM fields, science, technology, engineering, mathematics, which, these kind of fields always seem like they are very, very difficult. So if we can make it look a bit easier by teaching things very quickly, I think that really helps. Also, to be honest with you, making graphics and looking at other people's graphics, it really, really helps scientists themselves to understand the bigger picture. Today, I think we have an issue. We don't have to convince people of things like, sadly we do. I was going to say we don't have to convince people that that we're orbiting the sun, but some people you still do. But today we have a problem where the signal to noise ratio, I think, is decreased. So there's a lot of competition out there to get your voice heard, and scientists, I think, tend not to have much time to do it. There's only about, by the estimates I could find online, maybe about 15,000 astronomers in the world, which is roughly about 1 in several 100,000 people. There's plenty of people out there that want to hear about astronomy, but there's not many astronomers doing it, which is why outreach is very important. So I'll talk a bit about my research now, just quite briefly, actually. So I'm a ground-based astronomer of Jupiter and Saturn, occasionally Uranus, and even less occasionally exoplanets. These are planets going around other stars. This is a picture of me at the top of Mauna Kea, which is a mountain in Hawaii, which has about 13 of the world's largest telescopes on it. And what I do is I use telescopes to look at Jupiter's aurora. You can see the aurora in the top. This is raw data, by the way. This is an infrared view of Jupiter. You can see Jupiter is rotating around. It's all jumpy, and that's just the nature of, I wanted to show you really what we actually see during a night. This will be corrected for science later on. There's the great red spot going through as well. Let me just go back. There we go, play it again. See the great red spot going past. There's a moon flickering in and out of view as it orbits the planet as well. I also look at Saturn's rings, and I'll be talking about that next. But firstly, just to let you know where I've been in my career, I started at University of Aberystwyth University. That was where I got my undergraduate degree. Then I got my PhD at the University of Leicester 4 years later. Then I was over at Boston University in the United States. In 2016 is when I left there. Then I started at NASA Goddard Space Flight Center. And that enabled me, due to the timing, enabled me to see the James Webb Space Telescope while they were doing tests on it. So this is a picture of the James Webb Space Telescope before they sent it out into space. And if you look closely, you can spy a young postdoc looking to take a picture of himself, to have shared the same panels as all the beautiful images you see from space today. Thank goodness that mission worked and I didn't crack the mirror or something like that with my face. But yeah, it was really nice to see it there. And then after my stint at Goddard, I went over to Japan for 4.5 years, working for the Japanese space agency, JAXA. And they do lots of cool stuff, mostly in the business of being really good at collecting asteroid material from space. And actually, I had the pleasure of holding some asteroid in my hand. They didn't let me take it here, though. Oh, yeah, and now I'm at the University of Reading, kind of come full circle back to the UK. It's been about 10 years since I've been out of the country. I do hope I haven't missed anything in these last 10 years. But yeah, so now this sort of segues me a little bit onto, how did this research, because I'm a planetary scientist. At the time, I didn't do much in the way of outreach, I would say. But my research inadvertently led that way. This is unexpected. At the end of 2018, we had a paper coming out about Saturn's rings. So this is my excuse to tell you about my research a little bit deeper. Saturn's rings are falling into the planet at a rate of about 1,000 kilograms a second. And that's enough to fill an Olympic swimming pool every 15 minutes. So the rings are falling into the planet, and I'll tell you how that actually happens in a second. So while we were gearing up to show people this, because I think, just telling you that is not enough, in my opinion. We, as a team, we competed for time from Goddard Space Flight Center. They have a media department. We asked them if they could, produce some cool graphics for us. And actually they said yes. Often they say no, because they have to produce cool graphics for other people who are doing black holes and all sorts of things. It took about 3 months of back and forth, actually, to get the graphics ready, and we had to sort of delay the paper slightly so they could both come out at the same time, to which the journal were absolutely fine about. They love delaying, but it took about 3 months to produce, yes. And this is part one of it. So here you can see this is a zoomed in view of the rings. The rings of Saturn are made of countless shards of ice. It's literally made of water, by the way. Estimates are over 95% water, water that's frozen. Whoops. And they range in size from sort of sand grain size all the way up to bus size chunks of ice. So that's the environment of the rings. And they're not just sitting there, though. They are affected. They're bombarded by tiny meteorites and also extreme ultraviolet light from the sun. And those two things can actually lead to some of the smaller parts of the rings becoming electrically charged. You can just think about it as they're being bombarded by tiny things, and it's causing some static buildup. And a consequence of that is that when these small grains are electrically charged, that means they can finally feel the magnetic field that is penetrating through the rings, which I'm not sure you can see in this graphic, but you'll see in the next one. Yeah, so, oops. There we go. So here's the rings of Saturn literally falling into the planet. And they take this unusual path. It's not the way you might expect, right? It's not a straight line going into the planet. These are electrically charged particles. They are stuck to the magnetic field. And so they spiral in to the planet at these two places. And this is something that we saw with our telescopes in infrared. We actually saw these unusual bands. And that's what told us that there was something going on. And that's when we backtracked and found out that, hang on a minute, to explain this, we need a lot of stuff, 1,000 kilograms a second, coming into the planet at these locations. And so this is what it looks like. This stuff comes into the planet. This is ice. So it starts to get heated up in the upper atmosphere of Saturn. And then it sublimates. It goes straight from a solid into a gas. And that's how it's deposited. So it's sort of, I guess, more of a hail than a rain, but it's got a ring to it. And I wasn't planning to make that pun, but yeah, this is Saturn's ring rain, and it's an amazing mechanism. And the consequences are dire for Saturn's rings. That means that because of this mass loss rate of the rings, that means that they'll only be there for another 300 million years or so. And I know that sounds like a very long time, but it is less than 10% the age of the solar system, 4.5 billion years. It's about 7% the age of the solar system, actually. And really, 300 million years is kind of an upper estimate. We think that they probably have less than that. So we're really just talking a few percent of the age of the solar system. I think it's a short life for one of the solar system's most magnificent structures. It raises the question, what will Saturn's rings look like in the future? And bear in mind, our paper was due out on Monday, and this is a Friday. I had this thought, oh, what would they look like in the future? So I can't imagine. It already took 3 months to get all the animations out from before. Now I'm going to come up with this idea on a Friday. Saturday and Sunday is not really a working day. Is it too late to do anything? Definitely too late for me to ask the media team to do anything else. So what I did, kind of a quick and dirty thing, was to find an image of Saturn taken by the Cassini spacecraft. And this is quite a rare image. This was taken top down. You don't really get this view from Earth, obviously. You need a spacecraft to fly above. So I found this image, and basically I just used Photoshop to Photoshop the inside of the rings out. And then I used an online browser program called easygif.com, which was my way of just transitioning from one image to the other and showing them fading out. That on its own would have been enough, but I still had the whole weekend. And this was before I had kids, so there's plenty of time. So I started dabbling in, and this is not an advertisement, Adobe's Creative Cloud, which have dozens of programs that I already had access to. And so I tried a few programs, and I ended up using, whoops, oh, look at that spoiler. Let's see, let's get that to play. Well, yeah, okay, this, this isn't playing. It doesn't really need to play anyway. This is just an example of the interface in Adobe After Effects. It's not normally done for animations for space. It's normally done for sort of complex video editing. What it's doing on here, if it played, was it would show you how it tracks individual features, and you could. It's very clever, but this is not its real design purpose. But yeah, after a couple of days wrangling with that, by Sunday I had this animation made, and I showed what Saturn would look like in the future, the way that it was in my head. That's what I wanted to tell people. It doesn't, the rings of Saturn don't completely disappear. There's still probably going to be a little bit of debris left over. And if you know your planetary astronomy, you might know that Jupiter currently has a ring that doesn't look too dissimilar from this. I'm purely speculating. Maybe it had a bigger ring in the past. It probably did. That's my professional opinion. And Uranus and Neptune also have rings today. They're a lot thinner than Saturn's. And also, just throw it out there, Mars will also highly likely have one in the future when Phobos breaks up in about 30 million years or so. And so, yeah, this is the demise of Saturn's rings. And I managed to include this in the press release materials that are coming out on the Monday. They were up really early on the Monday at NASA, actually, to be able to stick that video in. And then to my surprise, New York Times actually put it on the top of the article about our work. As soon as I clicked on it, I thought, what? That's crazy. That's the first animation I ever made. And there it is within a couple of days. And it really made me think that animations are a really powerful tool for helping you to explain instantly what is going on. After that, the US government, it was the same week, actually, the US government shut down. At this point in time, I was working at NASA, which is a US government agency. And so they told us explicitly to not come into work and don't even check your emails. And we all said, okay. We were paid during that time. It was a little bit uncertain whether or not we would be paid, though, until the end. But yeah, so that lasted for a good 35 days. We didn't know it would last that long, honestly. Pretty much the whole of January was wiped out. And so I decided to dabble a little bit more in the animation business, since it was quite fun to do. I wanted to find a video, sort of by chance. I just wanted to find a video of all the planets rotating at their relative rates, because I thought it would look cool. So you have the Earth rotates in about 24 hours, and Jupiter is under 10 hours. And obviously I studied Jupiter, and the enormity of that, the difference, the Jupiter is about almost 2.5 times faster rotating than Earth. I just thought that was special, and I thought I would love to see that, as an actual rotating thing. So over the Christmas, New Year holidays, I was playing with the idea, and I made this video that I thought needed to exist. And it's the 8 planets rotating at their correct rates. And when I say correct, it's the relative rates are correct. So usually I'm doing, in all of my animations, something like 10 hours per second. So Jupiter in this animation is rotating around in 1 second. That's to represent 10 hours. Earth is 23 hours, 56 minutes. I'll get onto that later. And yeah, here are the, here are the different rotations and tilts. They're all accurate. The tilts are actually relative to each planet's orbit. That's the kind of one of the really important things that comes up here. You say, oh, there's no up in space and everything. I'll get to that. Don't worry about it. You can see that Uranus is firmly on its side, and it kind of orbits like a bicycle wheel around the sun. I posted that onto Twitter, and at that time I had about 400 followers on Twitter. They were mostly just friends and colleagues, and I'd often post before this for maybe a couple of years, maybe a few years. Every so often I would post this big space thread. I would spend hours on it, researching it and posting lots of things, and I'll get maybe 1 like or something like that. And I thought, yay, that's great. But, a bit deflating. And then when I put this one up, it got 1.6 million views in a day. And I thought, okay, it wasn't the case in this case that there was only one like. It was quite ridiculous, and I gained several thousand followers like instantly. And the government was still shut down, so I could still play around with this stuff at the time. One thing I did forget was I didn't put Saturn in this hashtag. Saturn being the planet that I study, I should probably have put that there. But hashtags, they're kind of old hat now anyway. But what it does, this kind of thing, this animation spawns spin-offs. I kept getting the same question again and again and again. Hundreds of times the same questions came up, and I had to sort of explain, and I kept explaining with words when really I could maybe make an animation to explain it better than I could do with words. So people are asking, why was the Earth rotating at 23 hours, 56 minutes? So what I did, everyone's used to it being 24 hours, but it's a 24-hour, the 24-hour day is relative to the sun. Best if I just show you the animation, to be honest. This is why I made it. So you can see here's the Earth, and it will rotate 360 degrees whilst it's orbiting the sun. Okay, so it's moved around the sun a little bit, and it's completed its full orbit, but the sun is not there. The sun is not overhead yet. Now it is. It's overhead now. That's 24 hours. So you can see why you can actually have two kinds of day. You can have a sidereal day, which is a day that is relative to the fixed stars in the background. And you have the solar day, which is relative to the sun. It's just a consequence of us orbiting the sun that we have these two different kinds of day. Following that, I've made probably about 100 different videos, maybe about 70 of them original, and the other 30 are usually upgrades, consistently upgrading again and again. These are the videos that Lucinda was talking about that are used all over the world at the moment, which was very, very surprising. I started upgrading them. I started making them cleaner and brighter. It helps on sometimes perhaps dim projector screen that I brighten these up. I was realizing that 70% of people looking at these animations are usually looking on their phone. I think it's actually 75% looking on their phones, and we haven't all got fancy new phones that have long battery lives and with the brightness on full. So I had to sort of make everything brighter and more vibrant so that it corrects for people's technology, basically. But here you can see one thing that stands out is Venus looks like it's rotating upside down. It's kind of either rotating backwards or it's upside down. The field isn't really settled as far as I can tell on what's happening there. Uranus as well is similar. It's on its side. Why is it on its side? I'll explain that soon. And why do the planets spin at all? And why do they all spin the same direction? There's so many sort of spin-off questions that come out of this, and I won't be able to address all of them in this talk in one shot. I'm pivoting here to Daft Punk, who a few years ago had a track out called Get Lucky. And the thing I like about this is that the lyrics at the beginning, I'm not going to sing it, don't worry, but what it is, what keeps the planet spinning, the force from the beginning. And I thought, okay, that's brilliant. This track, at least on YouTube, was viewed 777 million times. So there's a lot of people that have heard that the planets are spinning from the force from the beginning. So that's kind of my segue into talking about the solar system in the beginning and looking at those forces. I'm going to tell you how the planets rotate. So firstly, a giant cloud of gas and dust, mostly gas, was compressing, and it became flat, and it started rotating in this anti-clockwise direction. And I'm saying anti-clockwise, assuming that we're looking at this with today's Earth north. Don't worry about it too much. But we're looking at this system from the top as we know it today, is what I mean. And new planets are being birthed within this cloud of dust here. So if you see this planet on the left, yeah, it's a small planet on the left. It's carving out its own path. It's gathering up material from around it. It's getting bigger and bigger. We're going to call that planet baby Jupiter. And we're going to look at how it is getting its rotation from this system. So I think we're all okay with the whole system rotating anti-clockwise. It could have gone the other way. It really could have. It just depends on what the sort of the wind conditions were in interstellar space at that time. But it looks like in our system, we are spinning this way. That's fine. What happens is, and I'm going to zoom in, this is probably the most technical part of the talk, but let's just zoom into this area here. This is baby Jupiter inside this big rotating cloud of gas and dust. It's trying to form right there. What's happening is it's picking up its rotation speed from the gas that is moving around it. Okay, so this is the same for all the planets. So our assumption is, and I think it's a very valid one, that all of the planets in the solar system are picking up the same thing. There's no reason for them not to, unless they're hit by something. And so if you see outliers, if you see something that looks like it's rotating the wrong way today, something cataclysmic has happened to them. It could be a collision. So looking at the case for Uranus, there's a fantastic simulation showing what happens when you hit Uranus in the past. This thing hitting Uranus is the size of Earth, almost completely exactly the same size as Earth. If you look at the top left, you'll see a timestamp here in hours. So this collision is taking place really, really quickly. This is only several hours have passed, and Uranus is completely. It looks like it's completely obliterated, but most of it will recombine thanks to gravity pulling it back into place. But what that will have the effect of doing is actually causing Uranus to become tilted. So this is one of the hypotheses for Uranus tilt. Basically, something has hit it. Possibly more than one thing has hit it. This is largely the case for Venus as well. Well, if you ask any planetary scientist that studies Venus what happened, they might say either it was a giant impact hit it in the past, or multiple impacts, or something weird to do with its atmosphere rotating against the surface of Venus and making it rotate the other way. It's either upside down or it's rotating backwards. So now I'm going to talk about scale, because what I didn't include in those previous diagrams, the 8 planets rotating, was the actual physical size of the planets. And the main reason I didn't do that straight away was I thought that it would look weird. I thought you wouldn't be able to see anything. But I did it anyway. And I will start this. Ceres is a dwarf planet, much like Pluto. By the way, I put that in there for fun, and the moon as well. So this is to scale all of the planets and the moon and some dwarf planets rotating at their relative rates. It might be a little bit jumpy, but that's just because I'm trying to fit the whole solar system into one slide here. And there you see Jupiter. That's the rotation that I'm talking about. It's been in my head since before I made this animation, and I thought, it's so much larger than the Earth, but it's also rotating much faster than the Earth as well. So it's the fastest and the largest planet. And here's the sun as well. This is all to scale. The sun here is also rotating. I put it, the sun rotates in about 25 hours, but actually, just to be a bit more complicated, the sun is very special and it rotates something called differentially. So the poles rotate a little bit slower than the equator. The poles are about 34 days or so rotation period, and the equator is about 25 days. I put all of that together in one shot. And again, this is something I didn't think would really look very good. I didn't think that you'd be able to see Earth and appreciate it. And you can probably tell from the size of Pluto and the size of the rest of the gang, you don't really you can see why it's not a planet, right? But honestly, I don't mind if it's a planet. I'm not going to get into that. I know it gets very heated. And so, yeah, here we have Jupiter rotating faster than everything else. And it's also the biggest. So that begs the question, why? How is the biggest thing the fastest at the same time? So I'm going to go back to the early solar system again. And so here's Jupiter spinning around in this environment. Yeah, this time you can actually see it really easily, I think. And so, as I said before, it's gathering material from its environment, and that material is itself revolving around the sun. So as it's collecting that material, it's not just discarding the momentum that material had, it's actually gaining the momentum of that material too. Best demonstrated by this video here, where you can see when she's got her arms outstretched, she's moving slower, and when she brings them in, she moves faster. So this is basically what we call conservation of angular momentum. So if she had arms that were twice as long and brought them in, she'd be rotating even faster. Okay, so that's kind of what Jupiter did. Jupiter is bigger, it has more mass, it can collect from further away and bring in more material. So the bigger you are, the more material you can then possibly gain. And so the faster you can spin. So that's why Jupiter is fastest and biggest. It's not a general rule. Well, it's, there's going to be other factors at play that are going to sort of ruin that. Like Ceres is a dwarf planet that rotates faster than Jupiter, for example. And that's okay. You can just have an impact and explain everything. That's what we usually do. Okay, so I'm going to talk briefly about distance scales. Just double check the timing here. Yeah, good. Okay, so here is the Parker Solar Probe. It's a probe designed to touch the surface of the sun, they say. It's going to go extraordinarily close to the sun, closer than anything that has ever been to the sun that we've made anyway. It's the fastest spacecraft ever because it has to be. If you're going to go that close to the sun, you better be going fast, otherwise you're going to fall in it. So Mercury goes much faster than Venus. Venus goes much faster than Earth, for example. And this spacecraft moves at its fastest, something like, well, so far, there's different ways to say this speed, really. 635,000 kilometers an hour, which is 177 kilometers per second, or 395,000 miles an hour, or 110 miles per second. Think of anywhere that is 110 miles away from you right now, and imagine getting there in 1 second. That's so extraordinarily fast. That will get you around the Earth in about 4 minutes. That will get you to the nearest star in 7,100 years, though. So you note that even though that's really fast, even our nearest star, it will take you over 7,000 years to get to at that speed. That's the despair of distance that I'm trying to communicate next. So let's talk about the speed of light. Let's go faster than that. The speed of light is that. It's a very large number, like 1 billion kilometers per hour. So that is 1,700 times faster than that spacecraft. Okay. At this speed, you can get to the nearest star in just over 4 years. Again, there's other ways, other units, depends which units you like, lots of units. Now, I want to talk about, I'm going to offend everyone from sci-fi in one shot here. So people are in sci-fi traveling to other star systems within days. It's overly fast, but that's for good reason. It is for good reason. Otherwise, it would be unwatchable, wouldn't it? If you're going anywhere in like the speeds of our fastest spacecraft ever launched, wouldn't even get to the nearest star in 7,000 years. That is not going to be very good Star Trek. So what they've done is they've developed things like warp drives, hyperspace, and all that kind of stuff. Typically, I think Star Trek goes at about hundreds or thousands times the speed of light, and things like Star Wars might go in the hundreds of thousands to millions of times faster than light. Basically, it's the speed of plot. So I've always thought that, this is definitely necessary, but I've always also thought that, it makes people have a collective mental view that is a little bit flawed, because it makes you feel like things are closer together than they really are, because that's the main thing out there right now is awesome sci-fi. It makes you definitely feel like things are very close, but in fact, everything is terrifyingly distant and huge. But I felt like a lot of other people didn't think that way, so that's when I decided to start scaring people with things like this. Okay, so if you're going, and I made this kind of as a joke, I almost didn't post it. I was 50-50 on posting it. In fact, I didn't post it for a whole day while I was thinking about it, but I posted it anyway. It was the speed of light around the Earth visualized to scale, and I'm glad that plays okay, because it is very fast. It goes around the Earth 7.5 times every second. I didn't think we would be easily able to perceive it. That's why it was a bit of a joke. And then we can then go ahead and go to the moon at light speed. That's a little bit easier to see. So this is to scale, right? So the Earth and the moon are to scale. The distance is to scale between them. And time is also to scale in this diagram. And I'm going to launch a small piece of light out to the moon from the Earth. And there it is. It looks like there's some kind of weird quantum effect going on here. It's one piece of light, but that's just a bit of lag. There we go. It's smoothing out now. So yeah, when you look up at the moon at night, the light that you're seeing took 1.2 seconds to reach your eyes. And so, that's a real communication you have. You're also emitting in infrared. Some of that infrared goes out to the moon and hits it as well, 1.2 seconds later. So you are sort of physically, in a way, connected. I think that's what I like to think. While I have the Earth and the moon up there, I should also tell you that this distance is very large. You can fit all the planets in the solar system between the Earth and the moon. You can do this in so many different ways. In this case, I decided to tilt Saturn's rings like that to fit them in. This is not a stable system. All the objects can fit with room to spare as well. You can fit another half of an Earth in that space as well. So it's a very, very large space. Many diagrams out there, they have to put the moon and the Earth very close together. Otherwise, you just won't see anything going on. We can then go all the way to Mars. Now, these distances and times are to scale again, but in this case, I've had to make the Earth and Mars bigger, 20 times bigger, just so you can just about see them. I didn't have to do that, but can you imagine if I didn't? You would just see a label, really. So I'm playing this animation right now, and you can actually see that when the Earth and Mars are at their closest to each other, they are about 3 minutes away at the speed of light, 54.6 million kilometers away from each other. This is light moving over to Mars. This is the best possible scenario as well. It can take over 20 minutes to send a signal to Mars. This is not conducive to a good video chat with an astronaut on Mars. You'll just be, it's interesting. It kind of goes back to before we had telegraph poles and everything. We can back to letters again, practically. You'll just be sending a package, which is a video, and then have some time to think about a response, send it. Yeah, so this is the sort of the problem with the distance between these two things. Then this is kind of the famous thing people like to say is that sunlight takes 8.5 minutes to get from the sun to Earth. And this is a real animation. I'm playing it right now. You can see this bit of light leaving the sun and going to Earth. The fact that you can actually see that was surprising to me. I don't think I expected to see that when I made this. Other people also say that before this bit of sunlight left the sun, it was also traveling around in the sun for hundreds of thousands of years before it left the sun. Actually, there's an issue with that, but I won't get into it. Here is, let's go as far as we can with this. Okay, so here's everything to scale except for the sizes of the objects, which, as I said before, I have to make bigger so you can see them. Yeah, this is going from the sun to Pluto, which is a 5.5 hour journey. This is something I'll leave on for, I guess, until 6 p.m. So I'll see you later. No, this isn't an animation. It would have destroyed this presentation to even include it. It's available on YouTube though. 5.5 hours of, I've got free music on it, as much as free music as I could find. That only gets you to about Jupiter though. Yeah, so let's just throw that away. And I'm gonna sort of pivot over to some explainers. These are the things that come up on the side, things I've always wanted to see. So this is a demonstration of the orbits of the planets. So what I'm going to do is sort of have a race of all the planets here going around the sun. Because I wondered what it would look like if you could put something like Venus and Earth next to each other, if you could actually put them together at the real speeds that they're going at. You know, we know Venus would win because it's closer to the sun. If you're closer to the sun, oops, start that again. There we go. So here we go. They're off. A little bit jumpy. There's Mercury is winning. I'm just going to have them go around again because they are orbiting in a circle. So this is the relative orbital speeds of all these worlds as they go around. Neptune is not completed yet. Saturn has just finished. Yeah, Uranus and Neptune very slow. And these diagrams have got lots and lots of information on the sides. So you can stare at them for ages. They're all on YouTube. I'll give you a link later. It's basically youtube.com/interplanetary, all one word. So it's quite a simple one. But yeah, this is the kind of fun I've been having with these animations. Mars retrograde. This keeps coming up all the time. Mars and Mercury in retrograde. I'm not an astrologer. I'm just going to say that, obviously. But you know, I felt the need after so many people mention retrograde to explain what that actually looks like. How do we get retrograde? So if you're looking at Mars diligently every day, sometimes you'll see it every day. It moves, it advances in one particular direction in the sky. Sometimes for a period of time, it looks like it's reversing and going back the other way, which is ever so confusing. So this is what's happening. I got the date on the left there. So you can see Earth is the blue one, Mars is the red one. Here we are orbiting. This is the view that we have. Oh, look, you can see Mars is going the other way. That's because we've overtaken Mars in our orbit. It's like we're a train passing faster on an inside track or something. I could have said car. I don't know why I went to a train, but yeah, you can see that's how that retrograde is formed by the orbit of the two planets. It's quite simple, and as far as we know, it doesn't have an effect on human affairs, except if you are someone that likes to make an animation. That affected my week that week when I made this animation. So here's another fun one. So this is, what if you drop a ball 1 kilometer above the surfaces of all the planets? And you know, planets were not enough. I wanted to include the moon, obviously, and then I wanted to include the sun. And then I couldn't get away. I honestly can't get away with not including Pluto in a lot of things. If I include Pluto, a lot of people get mad that it's there. If I don't include it, a lot of people get mad that it's not. And that it's really split 50-50. So I just include it, but I just don't call it a planet. I'm just saying it's a solar system body. That's why a lot of my slides say solar system bodies. I'm just feel like a lawyer, how I've lawyered my way out of this or something. But yeah, let's let these balls drop 1 kilometer above these bodies. So there we go. The sun, you know, that wasn't long at all. 2.7 seconds to go 1 kilometer falling down on the sun. Jupiter's say a distant second, 9 seconds it took, and Earth is about to fall. There we go, 14.3 seconds. This gives you sort of an idea of the gravity of the situation. So, and there's Mars quite a lot later. So how long did it take for Mars? 23 seconds, yeah. I don't remember a lot of these values like offhand, so it's kind of a useful thing to have an animation to refer back to. The moon, on the moon, it's only just fallen. 35 seconds it took. It's worth noting that even though it took so long on the moon, the final speed that it landed with was 203 kilometers an hour. I guess that's about 120 miles an hour or something like that. So, you know, in some places in the solar system, you can spend ages falling. Like, there we go, Pluto is just finished. Nearly a whole minute it took for that same journey that on Earth took 14 seconds. But it still landed at 122 kilometers an hour. So I don't know, if you ever find yourself falling into Pluto, you've got a lot of time to contemplate your demise. Oh wait, Ceres hasn't finished. I didn't even see that. Ceres is smaller than Pluto. It's in the asteroid belt between Mars and Jupiter. And the ball that I dropped there is about to fall. There we go, 84 seconds. So that's I think a neat demonstration to show you, you know, what it's like out there. But I have some kind of more arty animations as well. This one shows you the rotations of all the planets, but on one sphere, because why not? It gives you an idea of the relative. It's almost like I need to put some WD-40 in it at the beginning there. But yeah, come on, Jupiter. So Jupiter is much faster than all the others. You can sort of see the rotation of Uranus and Venus going backwards in this animation. There's another way to do this. I'm honestly not sure which one I prefer to do. This one is kind of fun. You know, you can go, you can just spread it out like a world map view, and you can see the relative. Again, we need some WD-40 for this. And just before I go, I want to show you a correction to Huygens, if I may be so bold. Correct the scale diagram. Amazingly close, 1698. That's what they thought. The sizes of so that big circle is the sun, by the way, sun. And so what I've done is I used the old Photoshop and moved the planets to be their correct relative sizes. So maybe the second edition of that book, I'm not sure. Okay, so with that, I will, what I want to do is in the future, just tell you a little bit about the future. I've been spending the last year doing sort of proper animations, 3D animations. A lot of what you've been seeing is today, it's mostly kind of a 2D hacky version. It's enabling some pretty fun stuff. There are 50,000 planets being generated here. It's ridiculous. The tool I'm using next is called Blender, and it's great. So thank you, and stay tuned for some more from me, and the links are at the bottom left and right. And thanks very much.
Wonderful. Thank you so much, James. We don't have any questions online yet, so if there are any questions in the room, we do have our wonderful executive director here of the RIS who's going to help out with any questions.
So I first became aware that all these planets moved at different speeds only a few years ago, in the build-up to the great conjunction of Saturn and Jupiter. They appeared sort of just almost touching each other. And over an 8-month period, I was tracking them across the sky. I was interested actually that Saturn took that long to actually catch up with Jupiter. I wonder if you ever thought about making an animation of the great conjunction where Saturn was chasing up and caught him on the finishing line.
I actually did make about 4 animations for that in different ways during that period of time. December, wasn't it? December 2021? 21st. Right. Okay. Yeah, that's right. Yeah, I made a few animations for that. I can send them to you later if you want. And yeah, there was different ways to show it. At first, I had a line drawing between Jupiter and Saturn. It looked a bit odd. It looked like one of them was throwing the other one around, so I avoided that. And I had one where I put the moon in the background just so we could understand the distance between them. There's a few of them out there, yeah. But yeah, it is fun to do things for events that are currently happening as well. Yeah. Oh, I need to do an eclipse one, or eclipse one as well.
Okay, I have a question from Paul Roche online. I'm going to unmute his mics because it sounds like, and allow him to speak. So go ahead, Paul.
Oh, hi. Your animations are fantastic. So I use them a lot whenever I can. But because we do a lot of work in schools, and a lot of schools will block YouTube access, we often can't use the animations kind of directly in a school environment. So I'm just wondering, is it possible to access your videos and animations any other way than via YouTube?
Yeah, that's a good point. So initially what I used to do is I'd send out a link to my Google Drive and people would go on there, but Google kept telling me not to do that, I guess, automated. They said that there's too many downloads from there and it was going to block my Google account. So I stopped doing that, except for if people send me an email, I send them a link to the resources. That's probably happened about 100 times. And with that method, people have been able to download them sort of dispersed throughout the year evenly, I guess. But no, you're right. It would be good if I had some kind of repository to put them. I think, yeah, maybe I'll stick them on the RAS website. There we go. I just volunteered you.
Yeah, the RAS do have a facility, I think, don't they, to host materials. So it would be a great use for that. I mean, I'm sure a lot of people would then access them that way that couldn't access them through YouTube, maybe.
Yeah, it's a good point. Yeah, thanks for raising it. Yeah, I'll try and figure out a way. But in the meantime, yeah, feel free to email and I can send you a Google Drive link to about 60 1080p animations.
Great. Thanks very much, James.
Thank you, Paul. Here at the RAS, we'll have a chat with James afterwards about putting it up on the website.
Hi, and thank you for making all of this wonderful material. As a teacher myself, I'm very grateful for the hours that you've spent that make my job easier. I have a question. There's something on the astronomy spec that I teach that I don't understand. Since you specialize in Jupiter, maybe you can tell us a bit more about this. So one of the things we have to teach is about theories of planetary formation and the current position of the planets in the solar system. And there's one idea that talks about the freezing line and volatile gases, one side and the other side of that line. There's another theory that has to do with Jupiter migrating. And I'd love to hear some more about that because I don't really understand the scenario. Thank you.
Yeah, I used to work when I was working at JAXA for the last 4.5 years. I was working alongside someone that actually models the solar system and how it formed. And I was kind of surprised by the variation in their community, the sort of the sub-community, you know. Some people think it formed completely differently to others. But yeah, essentially there's this ice line or snow line somewhere. It's kind of one of the reasons we don't really have any icy ring systems inside of the orbit of Jupiter, because they would just sublimate, they would just turn into a gas straight away. That's why Saturn's ring system can live today for a while. But yeah, in terms of migrations, there are a number of models. I think one of them is called the Nice model, or the Nice model, if you like, named after the city in France. But yeah, the migrations, they're quite complex. I would like to make a diagram to refer to show you, but basically, let's see, Jupiter and Saturn probably formed a little bit closer to the sun. It could be the reason why Mars is quite small. It's about half the size of the Earth, or it's a little bit smaller than that. It could be the reason why no planet formed in the asteroid belt. You probably know that kind of stuff if you've been looking, actually, though. What you really want is a more detailed answer that I would want to send you a plot for. Yeah.
I have a question on YouTube from Matthew Henson. Very topical question with the aurora and the coronal mass ejections we've had experienced in this month. They ask if the Parker Solar Probe is the fastest probe to touch the sun. Has the solar orbiter been finding solar wind without being damaged or destroyed by the coronal mass ejection? I don't know if you can answer that, but it would be interesting if you did any animations about aurora or CMEs.
Great question. Yeah. So also, hi Matthew. Nice to meet you. Hello. But the the aurora the other day were fantastic. I guess it was the other week now. And Parker Solar Probe, I didn't hear of any damage from it. I think it's quite resilient. I think what you tend to get with these spacecraft that are closer to the sun, or just looking at the sun in general, is you tend to get this big wave of static on the displays that they have. They do have to correct for that in some way. But as for the safety of Parker Solar Probe during that, I don't know exactly how they deal with, they have an amazing heat shield, that's for sure. But in terms of the electrically charged particles from the sun, I guess they're radiation shielded with typically you have like a vault-like structure that houses all the computers inside of a spacecraft, like the Juno spacecraft has a kind of a vault to survive the radiation environment of Jupiter. So that would be my guess. Yeah.
It is 2:00 now. If anyone has any burning questions, here's your opportunity to raise your hand before we finish up here. But one quick announcement is that our RAS librarian, Dr. Sean Prosser, has an exhibit up in the library on Saturn for James's visit today. So you're welcome to go there after today's lecture, and we can head on up to the library. So any last burning questions for James?
Not really a question, it's an observation. I think your signature is wonderful.
Thank you. When my wife said she was getting me a signature made, I said, oh, okay, that's great. And when she, I was going to go all the way back to the beginning. I don't know if it'll be able to see it again. Something that I never considered was to make the O, which is very clunky. When you actually try and write a signature and you've got O apostrophe right in the middle of your name, that's why I gave up years ago and I just had a squiggle. I'll get there. So what they did was quite ingenious, I think. They actually made, I probably should have just clicked like the first slide somewhere here. Okay, just a few more. Well, why didn't I put it at the... Yay, okay, bottom left, yeah. They turned the O and the D into Saturn's rings and Saturn, and I thought, that's amazing. I never thought of that, ever. So I couldn't not put it in a public talk, and now it'll always be in there in my talks, I think. So that's probably one of the best Christmas presents. It's good, isn't it? Yeah. I'm not very good at drawing it out myself. I tend to copy and paste the one that they provided.
Fun question, really. How do you feel about the recent update on the actual color of Neptune? How are you going to use it in the future? Because it will make it more difficult to tell them apart.
Yeah, isn't it surprising how azure blue it used to be? For this talk, actually, I've had these images in talks before, but I actually clicked on Neptune and I just sort of moved the slider to make it a little bit paler. But all my animations are showing. Let's see. I'm not going to click for too long again. But okay, moving on. Just a little bit. I should have done less. There we go. Oh, actually, no. Let's do the prime one. This one. Okay, so I've been up and down with what to actually put as the surfaces of these worlds. So Venus really in real life has more of a, like if what you really want to know is what it looks like if you're an astronaut in orbit right now on Venus. It's very bright, firstly, but it's mostly kind of white, like it's practically white. So this is not even the real appearance. It's just slightly off-white, a bit yellow maybe. Earth hasn't got any clouds on it in this. Mars is probably too red. It always is too red in the images. When the Viking images came decades ago, they were very, very red. I think what they've done since, I can't really speak to it with any authority really, except when you look at the images taken by the rovers like Curiosity on Mars, sometimes they have a little panel which shows you colors. So the camera will then look at those colors and calibrate itself. I guess they didn't do that back in the day, and that's led us to think that it's a lot more colorful out there. In the future, I want to try and make things more photorealistic. But yeah, sometimes you can't see, like for example, look at Venus here. This is the cloud level Venus. But in the prior animation, I had this, which you've probably seen before. So what you're seeing here, this is made by radar of the surface. This is supposed to be the surface of Venus. Yeah, it's there's many different ways to show it, but Neptune is way too blue in my animations, and there's so many to change now. Yeah, but I'll get there. It will be version 10, I think, of this animation, honestly.
Keeps you busy. Thank you so much, Dr. Donahue, and thank you everyone for joining us. Have a good day.
Thank you. Stop the shit. Right. Nice to meet you. There we go.
Where are you?
University of Reading.
Okay.
Yeah. Oh.
This is the host.
Yeah.